Dear students, welcome back to the second session of my presentation on work, power and energy. Earlier, we saw the basic concepts of work, power and energy with illustrations and the various units used in our day-to-day life. Now, we shall see the various types of energy, energy transformation and the law of conservation of energy between pages 29 and 45 in your textbook. So keep your book beside you for ready reference. Nature has provided us energy in various forms, namely mechanical energy, electrostatic energy, magnetic energy, light energy, sound energy, chemical energy, and so on. Now let's focus only on the mechanical energy. The energy possessed by a body due to its state of rest or of motion is called the mechanical energy. Mechanical energy is of two types, potential energy and kinetic energy. Now, what is potential energy? It is the energy possessed by a body by virtue of its position, like water at the top of a fall, or like in the case of a compressed spring. All these are examples of potential energy. Now let's see the expression for potential energy. Consider a body of mass m is raised to a certain height h from the ground. Now this body will possess potential energy by virtue of its position. The work done in lifting the body is stored as the potential energy in the body. Earlier we saw that work done is equal to force into displacement. Therefore W is equal to F into H. But the force acting on the body here is nothing but its weight acting downwards, which is m into g. Therefore, work done is equal to mgh. This work done is the potential energy stored in the body. Therefore, potential energy is equal to mgh. Now, potential energy is of two types, gravitational potential energy and elastic potential energy. Now, what is gravitational potential energy? It is the energy possessed by a body due to the force of attraction of the earth on the body. Again, the work done W on a body of mass m in lifting it to a height h is W is equal to force of gravity mg into displacement h. W is equal to mgh. This work done is stored in the form of gravitational potential energy, hence U is equal to mgh. Here capital U denotes gravitational potential energy. Now elastic potential energy. Look at the illustration. A rubber band is stretched. When an external force is applied on a non-rigid body, it gets deformed due to change in size and shape. On removal of the force, it regains its original form due to the property of elasticity. Now, some work has to be done by an external force in deforming the body. This work is stored in the body as elastic potential energy. Now moving on to kinetic energy. It is the energy possessed by a body by virtue of its motion. It is usually denoted by K. Example, a rolling ball. An athlete who is running has kinetic energy due to motion. Flowing water has kinetic energy which can be used to do many useful work. Let's derive an expression of kinetic energy. Suppose a body of mass m is moving with a velocity v is brought to rest by applying a constant opposing force. Let A be the uniform retardation produced by the opposing force and the body travels a distance s before coming to rest. Thus, the retarding force F is equal to mass into retardation, which is F is equal to ma. Consider this as equation 1. Kinetic energy is force into displacement is the amount of work the body can do before coming to rest. Kinetic energy is equal to F into S. Consider this as equation 2. Now, in order to calculate the displacement S, let's consider the initial velocity of the body u to be v and the final velocity v to be 0 since it comes to rest. Since A is retardation is taken as minus A, here the negative sign indicates negative acceleration. Now from Newton's third equation of motion, we have learned that v squared is equal to u squared plus 2as. Now carefully substituting, v is equal to 0, u is equal to v, and a is equal to minus a. Hence it will be 0 is equal to v squared minus 2as, or v squared is equal to 2as. Hence s is represented as v squared by 2a. Consider this as equation 3. Now substituting the values of F and S in equation 2, we will get kinetic energy is equal to F into S, which is ma into v squared by 2a. After simplification, kinetic energy is expressed as half mv squared. Students, please make a note. On doubling the velocity of motion of a body, its kinetic energy becomes 4 times, or in other words, a faster moving body has more kinetic energy than a body moving slowly of same mass. Now, are you ready for the surprise element, the brain teaser which is usually asked in the board exam? Then take page 42 and read the question number 20. How much work is needed to be done on a ball of mass 50 gram to give a momentum of 5 kilogram meter per second? Now, how to relate kinetic energy and momentum? Let's see the relation. Let a body of mass m is moving with a velocity v. Then its kinetic energy is represented as half mv squared. Consider this as equation 1. Also, we have learned that momentum is the product of mass and velocity. Hence, p is equal to mv, or v is equal to p by m. Consider this as equation 2. Now, when you substitute the values of v in equation 1, it becomes kinetic energy is equal to p squared by 2m, or p squared is equal to 2mk, or p is equal to square root of 2mk. Now coming back to the numerical, once again I repeat, how much work is needed to be done on a ball of mass 50 gram to give a momentum of 5 kilogram meter per second. Now in the problem, mass is given in gram, which has to be converted into SI system into kilogram, that is 50 by 1000, and substitute in the formula kinetic energy is equal to p squared by 2m. You will get the value of work done as 250 joule. Now students, before we move on to the transformation of energy, I want you to study the work energy theorem, different forms of kinetic energy, and the differences of kinetic energy and potential energy, which is in page 32 and 33 respectively. In our daily life, we require energy in different forms. Since one form of energy can be converted into another form, we can obtain the energy in the required form. Here we see some illustrations of how mechanical energy can be converted into electrical energy in windmill and generators. Also, how electrical energy can be converted into heat energy like in ovens and toasters. Some more examples of energy conversion. In loudspeaker and electric organ, from electrical energy to sound energy, and in electric bulbs, how electrical energy is converted to light energy. Students, go to the energy transformation and the illustrations given in figure 2.13, page 35, one of the probable questions in the board exam. Let's move on to the last section of this chapter, but the most important concept, the law of conservation of energy. Now, according to the principle, energy can neither be created nor be destroyed. It can be changed from one form to another so that the total energy remains constant. Students, in the universe, the energy occurs in various forms. The sum of all forms of energy in the universe remains constant. When there is a transformation of energy from one form to another, the total energy remains the same. That is, it remains conserved. If there is only an interchange between potential energy and kinetic energy, the total mechanical energy remains constant provided there are no frictional force. Now let's theoretically verify this for a freely falling body. Let a body of mass m be falling freely under gravity from a height h above the ground. That is, from position A, as the body falls down, its potential energy changes into kinetic energy. At every point of motion, the sum of potential energy and kinetic energy remains unchanged. To verify this, let us calculate the sum of potential energy and kinetic energy at various positions, say at A, at a height h above the ground, at B, when it has fallen through a certain distance x, and at C, on the ground. Now at position A. At point A, the body is at rest. Hence, its initial velocity u will be 0, and therefore its kinetic energy becomes 0. The potential energy is equal to mg into h, since it is at a height h above the ground. Therefore, the total potential energy and kinetic energy together is equal to mgh. Consider this as equation 1. Now at position B, when it has fallen a distance of x. Students, you visualize that the body has fallen from position A to position B. Now the new position of the body B is at a height h minus x above the ground. Since it is at a certain height above the ground, it will definitely possess potential energy. Also, since it has moved a certain distance from A to B, it will also possess kinetic energy. Now, potential energy by expression is equal to mg into h minus x. To calculate the kinetic energy, the new velocity acquired by the body in reaching B from A will be derived from Newton's third equation of motion, v squared is equal to u squared plus 2as. Here in our case it is written as v1 squared is equal to u squared plus 2gx. A is replaced by g since its acceleration due to gravity, and s by x, the distance through which the body has fallen. Hence, v1 squared is equal to 0 plus 2gx, or v1 squared is equal to 2gx, since the initial velocity u at A is equal to 0. We know kinetic energy is equal to half mv squared. Substituting the value of v1 squared, we get kinetic energy is equal to half m into 2gx. Now, total kinetic energy is equal to potential energy plus kinetic energy, which is equal to mg into h minus x plus mgx. Now, after simplifying, we get the total energy as mgh. Consider this as equation 2. Now at position C, let the velocity acquired by the body on reaching the ground from position A be v2. Then potential energy at C is 0 since h is equal to 0. And to find kinetic energy, we use Newton's third equation of motion, v squared is equal to u squared plus 2as. Here u is 0, s is equal to h, and a is equal to g. Hence v2 squared is equal to 0 plus 2gh. v2 squared is equal to 2gh. Therefore, kinetic energy is equal to half m into 2gh. And finally, after simplification, we get kinetic energy is equal to mgh. The total energy is equal to potential energy plus kinetic energy, which is mgh, equation 3. From equations 1, equation 2 and 3, we see that the total energy of the body remains constant throughout its motion. Therefore, the total energy is conserved. Students, now before we conclude, let me remind you need to go through the application of principle of conservation of energy to a simple pendulum in page 45, which is again a probable 3-mark question to explain how energy is conserved. This brings us to the end of the chapter. As usual, assignments will be uploaded in Google Classroom. Go through the lesson and get ready for another session as we move on to another chapter. Till then, bye for now. Take care.